Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So now we are going to be taking our last little look at a topic from Chapter 5. This is Section 5.9, Applications to Markov Chains. Alright. So here's the overall setup that we're going to be looking at. So what we're going to have is let's just say a population of individuals, each of which can be in one of a number of states. So let's say we have a population of individuals each of which belongs to one of several, could say states or categories. Let's say categories actually. Each of which belongs to one of several categories. So for example, category A, B, C, or D, each individual belongs to one of these. Then, so that's one part of the setup, and we have also a fixed, or a certain probability that an individual from one state, or from one category, will transition to another. And then the goal is to determine, based on an initial breakdown of the population, how the long run behavior of the system will end up looking. So the goal is determine the long run behavior of the population. All right, so as an example, let's just say that what we have is, let's say we have initially a group of people that are either single or married. So initially we have 100 PCC students. Let's say 50 of whom are single. We'll write S for that. And 50 of whom are married, which we'll write with an M. So we have two categories, single, married. And then let's say that out of the single people, each cycle, let's say each year, 20% of them get married, 80% of them stay single. So each year, 20% of single people by which I mean students, become married, implying then that also 80% stay single. And let's say 10% of married people become single. Meaning, in other words, 90% remain married. Okay, so this would be the kind of setup that we might have. We have a population. It's 100 PCC students. We have a certain situation where they can belong to one of two categories. In this case, let's say married and single. And then we have some overall behavior. 20% from single become married. 10% from married become single. Okay, so what does all this have to do with matrices, vectors, things like that? So the goal is to figure out what's going to be happening in this situation using the techniques of linear algebra. So, what will happen in the long run? Okay, so let's try to figure out the techniques that we'll use to answer a question like this. So first off, we'll need some definitions. And the first definition that we will create is probability vector. So probability vector. So what this means is it is a vector whose entries share the important properties of a probability distribution. So this is a vector. All of whose entries are non-negative, because negative probabilities are nonsensical. And the sum of whose entries is 1. So that's what it means to be a probability vector. So it's just like a probability distribution in that we do not allow any negative values, and the values have to altogether add up to 1. In other words, like 100%. So for example, a probability distribution or a probability vector could be something like this. V equals 0.3, 0.6, 0.1. So you'll notice no negative values here, and they all add up to 1. So this means, by the way, that none of the values could be more than 1, because otherwise they wouldn't be able to add up to 1 without the presence of some negative values. The values might be 0, that's okay, but they can't be negative. That's the meaning of non-negative as opposed to positive. Positive means not even 0, non-negative means 0 is possible. Okay, so that's a probability vector. Now, stochastic matrix. So this is a matrix, each of whose columns is a probability vector. And in particular, it's a square matrix. This is a square matrix. Each of whose columns is a probability vector. All right. Now, transition matrix. This is specifically a stochastic matrix that's being used to represent the transitions between one category and another of our population. So this is a stochastic matrix that represents the probabilities of transitioning between states or categories. And then the setup here, so we'll say P equals, and this is from category, let's say like A, B, C, and then over here to category. A, B, C. And the order has to be the same. And then let's say like right here, let's say just like this one as an example, this would represent the probability of going from category A to category B. So the probability of going from A to B, just for example. So as an example of something like this, so for the marriage example, married versus single, P, we always use P for these, P for probability, I guess. So we have from, let's say M and S to M and S. It doesn't matter which one you do first as long as you do them consistently. M then S, M then S. So this one would be 0.9 married, stay married. 0.1 married becomes single. Here, this 0.2 single becomes married, and 0.8 single remains single. Alright, now then the purpose of expressing these things via matrices is then what happens is you can accomplish the passage of time through the multiplication by this matrix. So then a Markov chain This is a sequence of vectors representing iterated transitions over time. And so we could say that this is we could say x0. This represents the initial state. And then x1 would be p times x0. And then x2 would be p times x1, or in other words, p squared times x0, dot, dot, dot. And we'll go to xk is equal to p to the k, x0. Where the x's here are usually going to be probability vectors, but they don't necessarily need to be. It doesn't always. It can make sense to use vectors other than probability vectors here, but it's customary to use probability vectors. All right. And now, to rephrase the goal of our investigation, we can ask ourselves if this sequence of vectors approaches any limit vector. So the question: will this sequence approach any equilibrium vector? Well, that all depends. That all depends on the nature of the matrix. So one more definition. Regular stochastic matrices. So what this means, what these are stochastic matrices of the form P where P to the K has all positive entries, in other words, no zeros. So a stochastic matrix always has non-negative entries, but it might have some zeros. So no zeros for some K. So if a matrix is regular, if a stochastic matrix is regular, then what that means is that there is some power of P that does not contain any zeros. And if we have a regular stochastic matrix, then we can actually figure out what's going to be happening in the long run, all based on what the eigenvalue of these of these matrices is going to end up being. So theorem. So theorem, if P is a stochastic matrix, then lambda equals 1 is an eigenvalue of P. And furthermore, if P is a regular stochastic matrix, then not only is lambda equaling 1 an eigenvalue of P, but the eigenvector that goes with that lambda equals 1 will be what is called a steady state vector that all the other vectors will approach in the limit. Then the eigenvector associated with lambda equals 1 will be the vector any Markov chain using P will approach. And that, importantly, is completely irrespective of what the initial vector was, the initial state. So irrespective. So no matter how the things were initially distributed, if you have a regular stochastic matrix, then over time there will be a limit that they will all approach, and it will be the same, totally regardless of the starting value. So the eigenvector associated with lambda equals 1 is called a steady state vector. Okay, so now let's go back to the problem of the married people at PCC. So let's find the steady state vector for this situation. So this is the married versus single. Oops. So P, remember, was 0.9, 0.1, 0.2, 0.8. And then the question is, find the steady state vector. Okay. Well, p minus lambda I would be 0.9 minus lambda, 0.2, 0.1, 0.8 minus lambda. Now for lambda equals 1, which we are always told is going to be an eigenvalue here. P minus I is just going to equal negative 0.1, 0.2, 0.1, and then negative 0.2. Now it's clear here that this is going to be a situation where it's going to row reduce to a row of zeros, and actually we can see pretty easily where this would be going if we were to set it up. So if we want to augment it with zeros, negative 0.1, 0.2, 0.1, negative 0.2. Oops, as I said, augment it with zeros. So we could scale both of these by a factor of 10. We can just clear out this, move this up here, 1, negative 2, 0, and then 0, 0, 0. And now here, if we look at it as x1, x2, actually I shouldn't call them, I will call them x1, x2. It's awkward because I was using the x's also for the sequence of the vectors, but that's customary. So here, x1 minus 2x2 equals 0, and so then x1 equals 2x2, x2 is free, so x2 equals x2, and so then that means that the steady state vector, which we'll frequently use a q for, q just because it's a letter close to p, and actually let's put that up here. Q is going to be our customary name for a steady state vector. Oops, x2 times 2, 1. Now, if we want to, so if we want this to be a probability vector, which we usually do, then we can, then what we can do is we can scale it. So scale this to make the entries add up to 1. So then we can go with q is equal to, well, currently the entries add up to 3, so that's what we divide by. They add to 3 currently. So you just add up the entries and divide by that, and that will scale the steady state vector so that it is a probability vector. And what this means is, in the long run, two-thirds. So we had our matrix oriented, so first was married, second was single. Of the population, will be married, and 1/3 be single. And what that means is in terms of actual people, so for our population of 100 students, if we wanted to actually scale it according to that, so then we have 100 people. 66.7, or let's just round it to the nearest person, because I mean, after all, we're saying it discretely. 100, about 67 will be married, and about 33 will be single. Now, if we want to actually watch this in action, what we can do is set it up in the following way. So here I have entered the elements of P in the matrix, or into the matrix form, and I'm going to store that as P. So just store, use the store button, and then alpha, find the button with the P on it, and put that in there. And then I'm going to set up the initial distribution of my students. It was 50 married, 50 single. So I'm going to set up a vector that represents that. So this is representing the state of my population at the very beginning. And now what I'm going to do to watch this all, my mistake, I meant that to be a column vector, so I meant that to be a semicolon. Okay, there we go, that's how I wanted it. Now what I'm going to do is I'm going to do alpha p times answer, so that way I'll be able to iterate over and over and over again what happens year by year. So right at the beginning here, we've got 50 married, 50 single. First is married, second single. Okay, so then a year goes by. So we've got 55 married, 45 single. So this represents 90% of those who were married staying married, 10% defecting to the single life. And conversely, among the single people, 80% of them staying single, 20% of them defecting to the married life. So then we repeat. Now it starts getting into fractional people. So obviously, if we were talking about actual physical people, we would round. But here, year after year passes, and you notice the number of married is going up, the number of single is going down, up and up, and the single is going down and down, and it just keeps on getting closer and closer and closer and closer to the steady state vector. And if I just keep on going, you'll notice that more and more of the digits start to line up with exactly that 2/3, 1/3 breakdown that our eigenvector analysis suggested. So we just keep on going. All right, and you get the idea. As we proceed, it iterates further and further and further, and by however many this was, it is almost exactly 2/3, 1/3, and that was totally irrespective of what the starting configuration was. So, for example, let's say that I had started it all single, 0 married. So what that would look like is 0 married, and then 100 single. So all single, no married. And if I did then P times the answer, and I let that iterate, let's watch what happens. So that represents the 20% of the single people getting married. And then you notice right here what we have is actually the switch of actually the final state. But you'll notice the number of married just keeps on growing, the number of single just keeps on decreasing. And you'll notice that it didn't take very many years to pass here before we approached actually the steady state figure, the same one that we ended up with on the previous one. So no matter how it started, it could all even start out as single. If this transition matrix holds up, then the long-term result will always settle down to that steady state vector. And the reason for that was that the matrix in question was regular. Now, what it means for a matrix to be regular effectively is that so there's some iteration of the probability matrix that will, after that many steps, make sure that there is at least a little bit from each category that gets scrambled around to each other category. This keeps them from all getting clogged up at one particular category. So it means there's open lines of communication between the categories. All right, let's try this again. Let's try another example of this, where what we have is a 3-by-3 situation where we have Democrats, Republicans, and other from one election to the next. So let's just say these are. So vote Democrat will be D, Republican will be R, O will be other. And of course, you could imagine a big involved story problem here involving all this, but we will just cut to the chase, and let's say that the probability, or sorry, the transition matrix. So this is from D, R, and O to, and it always has to go this format. It always has to be from as columns, to as the rows. And most importantly of all, the order has to be the same. The order has to be the same. DRO, DRO. Okay, so let's say we have 0.7 for D to D. So that means 70% of those who voted Democratic in one election will vote Democratic again the next election. Let's say 0.2. That's going from Democratic to Republican. And 0.1, that's going from Democratic to voting for some other candidate. And then let's say for Republican, let's say 10% will go from Republican to Democrat. Let's say 80% will go from Republican to Republican, so in other words, stay. And then let's say 10% Republican to other. And then for the others, let's say 30% of them might go from other to Democrat. Say 30% of them might go from other to Republican. And let's say 40% of them stay other. They were third party, they're still third party. And then let's say we want to find the steady state vector. All right, well, we can just cut to the chase here. P, so that means lambda equals 1. There's always lambda equals 1 here. So P minus lambda I is just really P minus I. We might as well just go ahead and augment it with the zeros now, since we know that's where this is all headed. And let's see what happens. So that's along the main diagonal. So that means we're going to have negative 0.3. We're going to have 0.1. We're going to have 0.3. Augment 0. We're going to have 0.2. We're going to have here negative 0.2. We're going to have 0.3. Augment 0. And then down here we're going to have 0.1, 0.1, and then subtracting the 1 we're going to have negative 0.6. Augment with the 0, and here we can do this by hand, or we can do it by calculator. it doesn't really make a big difference one way or the other, what way we go about it. The important thing is that when we row reduce this, we will probably scale it all by a factor of 10, and if you notice something that will immediately cancel each other, you can go ahead and take advantage of that, but it doesn't really make a big difference one way or the other. So I'm just going to go ahead and ask my calculator what the deal is. Alright, I spared you having to watch me enter our REF and then the matrix, but here it was, and here is the RREF version. And notice, because my calculator is a TI-89, even though its default is not to put in decimals, if you give it a decimal input, it will then assume that you mean to keep it in decimals, and so it will maintain decimals if decimals are entered. So 0, 1, negative 3.75, 0. And this row of zeros, if there were no row of zeros here, I would know something went wrong, because I would know then that that wasn't actually truly an eigenvalue. So all stochastic matrices, whether regular or not, have to have at least an eigenvalue of 1. Now, if they're regular, then that means that that'll be the long-run behavior of the Markov chain. If they're not regular, then not necessarily. But let's now think about what this means. So x1 is going to equal 2.25, x3. x2 is going to equal 3.75, x3. x3 is going to equal x3. So we've been down these roads enough. So we know that q is equal to something of the form x3, 2.25, 3.75, and 1. Now I want to scale it so that it ends up being a probability vector. So technically it would be okay to have something like this that would make sense as an answer. If you were just looking at ratios, you would know that, like, for every one other, there were 2.25 Democrats, 3.75 Republicans. But it would make more sense in a problem like this to then put it into percents rather than ratios. So currently they all add to make it looks like that adds up to 6. They all add up to 7. So what this means is that I can scale by setting x3 equal to 1/7, and that'll give me a q of 2.25 over 7, 3.75 over 7, and 1 over 7. Or in other words, if I wanted that as percents, or in other words as decimals, then I could just do 2.25 divided by 7, 32, I'm sorry, I should say 0.32, 1, 3.75 divided by 7, oops, divided by 7, gives me 0.536. And because of rounding, these may not exactly add up to 1 just because of the last digit. Oops. TI-89. Got to give it a decimal if you want it to produce a decimal. So then we have 0.143. So this district, oops. So assuming this was just like some little district. So this district in the long run, if these trends in transitioning would continue, so this district would approach in the long run, 32.1%, and so these are D, R, and O. They fit the same order as whatever however you set up the P. So would approach in the long run, 32% Democrat, 53.6% Republican, and 14.3% other. So that's what this is saying the long run consequences of this trend would be, no matter actually what the initial distribution was. Now, of course, it could take longer or shorter, depending on how close the initial vector actually was to this final configuration. But let's just see this. Let's just see this play out over the course of a few election cycles. And again, to spare you watching me type it all in, I have taken the liberty of entering in the matrix P and store, and then I hit alpha P so that it would in fact store the matrix as I wished. So that is indeed the original matrix P. Now let's give an initial setup of our district. Let's say that it was 1/3, 1/3, 1/3. So 1/3 Democrat, 1/3 Republican. So let's just say these are just completely fresh people. They are all equally likely to go for any party. They haven't had a chance yet to settle into their eventual patterns. They're just fresh out of the factory. 0.3, 0.3, 0.3. Okay, so this is our initial setup, and now let's say what I want is I want to do P times answer. So alpha P times answer. This way I can just hit enter to iterate over and over and over again. Okay, first cycle happens. So notice what happened here. First off, the number of other went down, the number of Democrats went up slightly, the number of Republicans went up a little bit more. Again, and what we now have is 36, 48, 16. Now we have 35 basically, 50, and 15. And let's just go a few more years out. And you'll notice that we are settling down now into the predicted number. So this is going to be the long-term equilibrium solution. It will be the steady state that this district will approach in the long run. Okay, so that's one use of eigenvalues and eigenvectors, is to analyze the long-run behavior of a situation involving these sorts of transitions between different categories of the same population. And that's going to end our investigations of Chapter 5. However, Chapter 5 material will be very present in the future for those of you who are going on to differential equations. That's Math 256. That's the class that will really dig most deeply into all of the eigenvalue type analysis. So to learn more about eigenvalues, eigenvectors, eigenspaces, and the like, stay tuned for next term, where Math 256 will take this topic up from a differential equations perspective. All right, but for now, this will do it for this episode of Math 261. I'll see you next time for section 6.1. Till then, bye.